Welcome back to this brief introduction to piezoelectricity, materials where a mechanical stress produces an electrical output and applying an electrical force produces a mechanical output. Now it's time to put that effect to use. You see, after this World War I comes around and there's a demand to detect submarines. They're becoming a very effective stealth weapon. They can move in, sink a ship and escape with very little chance of detection. This would have to change, and there was a great demand from the world's leading militaries to develop a way of detecting submarines. Sonar, in this case, was leading the way. The principle is simple: let off a sound wave through water, it returns an echo when it hits something. Then the distance can be calculated from the time between signal and echo. So you have a distance, you have a direction because your beam is directional, and therefore you have a relative position. It's brilliant. Initially, Paul Langevin and Konstantin Chilovsky used an electrostatic detector to detect the echo. However, they then turned to another method. You see, sending sound waves through water means you're sending a vibration. Remember, at the start of this video I described a piezoelectric material as one that would produce an electrical output from a mechanical stress. Vibration is going to cause a mechanical stress. So in the early development of sonar, piezoelectrics were very important. They competed with magnetostrictive devices, which are very similar, only with magnetic fields replacing the electric in piezoelectrics. These battled for supremacy in sonar use. Following these experiments, Robert William Boyle, who was working for Britain's anti-submarine division, used piezoelectric quartz to make a practical detection device, and these were successful in the use of sonar to track submarines. This led them to be used for other purposes. One interesting example that I quite like is the cartridges in phonographs. A record disc or cylinder has grooves, and the change in depth of these grooves is measured by a stylus. This change in depth is then turned into an electrical signal which can be amplified by a loudspeaker. And piezoelectrics, essentially for the same reason of taking a mechanical input and converting it to electrical, became a reasonably cheap way to do that conversion. So to sum up where we are now, we have practical use of piezoelectrics, both for the military and in civilian use. However, at this point something needs to be done for them to really take off. A piezoelectric device is only as good as its material, and the materials at that time were still in their infancy. For the technology to really take off, we need something better. We need larger displacements for a given voltage, for example. We need reliable mass production to drive down costs and standardise quality. So next time I'm going to talk a bit about the development of synthetic materials.